You may occasionally need to create scale-out databases so that duplicate copies of data reside in multiple places for performance or business continuity purposes. While this goal could seemingly be accomplished with traditional unidirectional replication, such an architecture would be unlikely to meet the needs of an evolving organization with multiple business units. Traditionally, this required difficult trade-offs between performance, cost, and data integrity. In some situations, routine maintenance tasks like database upgrades could become a real issue if there's significant downtime involved in the upgrade process. Hello everyone, my name is Shayon Sanyal. I'm a senior database specialist solutions architect here at AWS. I specialize in the Postgres database engines, including Amazon Aurora and Amazon RDS Postgres. In this video, we will learn about bidirectional replication solutions offered on Amazon Aurora Postgres that lets your databases scale out across regions and gives you a plan to be always up and running. So our agenda for today is we'll discuss what Amazon Aurora is. We'll discuss the distributed storage architecture. We'll cover some use cases for bidirectional replication. Next, we'll take a look at a few different ways of achieving this in Amazon Aurora Postgres. Finally, we'll take a look at a quick demo with a couple of solutions. Let's start with a short background on Amazon Aurora. Amazon Aurora is an enterprise database built for the cloud. It has the speed and availability of high-end commercial databases with the simplicity and cost-effectiveness of open source databases. This means that there's no licenses to manage and no licensing cost. It's drop-in compatible with two open source relational database engines. You can either choose MySQL or Postgres, which means that the code that you wrote for either of these database engines will continue to work with Amazon Aurora without making any changes. All of this comes with the AWS promise of simple pay-as-you-go pricing. Let's take a look at the storage architecture of Amazon Aurora. Amazon Aurora has a purpose-built log-structured distributed storage under the covers. Storage volumes get striped across hundreds of storage nodes. The bottom part of the slide with the orange boxes here represent these storage nodes. These nodes are machines with processing power and memory with locally attached, high-speed, non-volatile memory express or NVMe SSDs. The database doesn't really know the intricacies of this storage. To the database, this is simply represented as a cluster storage volume. We also continuously backup and stream the data and logs to Amazon S3 for additional durability. As part of the distributed storage architecture, we replicate the data 6 ways. Each page is replicated across 3 availability zones, with 2 copies in each availability zone. This helps us survive failure of an entire AZ plus an additional failed node. We segment the storage volume into 10 gig protection groups, and each protection group is made up of 6 10 gig segments. These are the 6 copies of replicated data that we discussed earlier, 2 in each availability zone. With Amazon Aurora, storage scales automatically in 10 gig increments up to 128 terabyte of maximum database size. Now let's talk about a few use cases for bidirectional replication. The most common ones include write scalability within a single region, write scalability across multiple regions, blue-green deployment, and zero downtime database patching. Now with the use cases identified, let's take a look at what tools we have in Amazon Aurora Postgres for enabling these capabilities. First, let's take a look at pglogical. The pglogical extension provides logical streaming replication capabilities for Postgres using a publish-subscribe model. The pglogical extension serves as a basis for many of the underlying replication technologies in Postgres today. Postgres is a very flexible platform, and we can configure 2 read-write instances in Amazon Aurora to work as a bidirectional replication solution without resorting to unwieldy triggers. In this architecture, each is truly an independent database, so your application must not depend on any kind of read consensus. Some of the key features for pglogical are: pglogical is Postgres major version agnostic. It's been supported in Postgres since version 9.4 and is still supported on later versions. There's no additional cost. It's offered as an extension. It's easy to set up and deploy and very well documented in the Postgres community. pglogical supports Aurora Postgres both as a source and a target. The pglogical extension can be used to migrate critical workloads, migrate data between Postgres major versions, something we call as MVUs within the Amazon Aurora ecosystem. It can also be used to replicate data between two or more Postgres instances regardless of where those instances are located. For example, you can have a Postgres instance on-prem and you can migrate data from on-prem to RDS or Aurora Postgres. You can also have data in the source on Aurora Postgres and you can migrate data off of Aurora Postgres to a self-managed Postgres. With pglogical, you can migrate whole clusters, specific tables, specific rows, or specific columns. You can also replicate specific parts of a schema to other systems for ETL, reporting, etc. Now let's take a look at some of the use cases for pglogical. You can use pglogical to migrate from older versions of Postgres into RDS or Aurora Postgres. You can use pglogical to replicate specific tables from source to target. You can also use pglogical for bidirectional replication between two Postgres instances. As you can see, it's the ideal choice for bidirectional homogeneous replication. It's important to call out that although pglogical is a powerful logical replication tool, it has a few limitations. Currently, pglogical replication and administration requires super user privileges. It may be later extended to allow more granular privileges. Unlocked and temporary tables cannot be replicated, much like with physical replication. pglogical works on a per database basis. To replicate multiple databases, you must set up individual provider-subscriber relationships for each. Updates and deletes cannot be replicated for tables that lack a primary key or other valid replica identities such as a unique constraint. Replication has no way to find the tuple that should be updated or deleted since there is no unique identifier. Automatic DDL replication is not supported. Managing DDLs so that the provider and subscriber databases remain compatible is the sole responsibility of the user. pglogical, however, provides the replicate DDL command to allow DDLs to be run on the provider and subscriber at a consistent point. For more details, please visit the link at the bottom of this slide. When would you actually choose pglogical for replication? You would choose pglogical when you need full database replication capabilities between two or more Postgres databases. And this database could be on-prem, it could be on EC2 instance, or it could be on RDS or Aurora Postgres. You would choose pglogical when you need selective replication of sets of tables through what we call replication sets. You would also choose pglogical if you need selective replication of table rows at either the publisher or the subscriber side through something called as a row filter. You would choose pglogical if you need selective replication of table columns at publisher side. And also pglogical does support advanced conflict detection and resolution capabilities. The best part, all of this comes for free. Now let's take a look at replication using Oracle GoldenGate for Postgres. Oracle announced the general availability of Oracle GoldenGate Postgres capture support last year. The GoldenGate Postgres delivery has been supported since GoldenGate version 12.1 release. And this allows users to replicate the data from GoldenGate supported heterogeneous databases, example Oracle, to Amazon RDS or Amazon Aurora Postgres databases. With GoldenGate 19c, it now also supports the capture of data from Postgres database versions 10 and above. Let's take a look at a high-level deployment architecture with Oracle GoldenGate and Amazon Aurora Postgres used for bidirectional replication. In this architecture, since this is a cross-region setup, we set up VPC peering between the source and target regions. In our example, this is US East 1 and US West 2. We then set up source and target bastion hosts on Amazon Linux EC2 instances to log in securely to another EC2 instance that has the GoldenGate software installed. We then set up the extract, pump, and replicate processes for GoldenGate on EC2 instances in those two regions. Next, we set up two Aurora Postgres database clusters in the source and target regions. Then we create source and target Postgres databases, tables, and users with required privileges. One thing to keep in mind is to ensure that your source and target tables have primary keys. This is primarily useful for CDC or change data capture. Enable logical replication by setting rds.logicalReplication parameter to 1 in the Aurora parameter group. Let's look at some of the reasons on when you would want to choose Oracle GoldenGate for replication. You would want to choose GoldenGate if your use case involves multi-master active-active bidirectional capabilities. If you have in-house Oracle GoldenGate skills, expertise, as well as existing GoldenGate licenses, that's another reason for you to choose this solution. If you need advanced conflict detection and resolution capabilities, as well as if you need some advanced functionality offered through integrated capture mode for certain database engines, this becomes a really good solution. All of this comes at a cost. Out of all the solutions, Oracle GoldenGate is the most expensive. Finally, we will take a look at some AWS partner network tools available on the AWS Marketplace for data replication. We will look at them at a very high level. HVR is a powerful software product that enables real-time homogeneous and heterogeneous data replication. HVR uses change data capture methods to replicate changes between databases, directories, as well as between databases and directories that HVR calls locations. HVR uses its own internal log mining technology along with certain database vendor APIs. The CDC method that HVR uses during a replication depends on various settings defined or configured within HVR. Stream's enterprise-grade streaming integration platform makes it easy to build continuous streaming data pipelines, including change data capture to power real-time cloud integration, log correlation, edge processing, and streaming analytics. Stream moves real-time data from virtually any data source, including enterprise databases, via log-based change data capture. With real-time data synchronization capabilities, Stream also helps companies move data from legacy databases to Amazon RDS or Aurora databases with near zero downtime and zero data loss, and enables an immediate switchover to the AWS environment. Click Replicate, formerly Attunity Replicate, is a data replication and transfer solution that simplifies and accelerates data migration from many databases to many cloud platforms. It does this efficiently and securely with near zero downtime migration and minimal impact. With log-based CDC technology, Click enables continuous replication to minimize downtime and reduce impact on source database systems. You can also use an intuitive and configurable GUI to quickly and easily set up data migrations with no manual coding. Let's look at some of the reasons on when you would want to choose an APN tool for replication. Typically, when you already have an existing relationship with an APN partner or a vendor, or are looking to develop a new relationship, this is when this solution will come in handy. When you need logical database replication capabilities with the ability to do selective replication such as filter tables, columns, and rows, as well as the ability to deliver changes in a heterogeneous environment, this is also one of the common use cases. When you're looking for more cost-effective options with similar change data capture capabilities and richer support for heterogeneous environments than that is offered by Oracle GoldenGate, as well as some multi-master active-active bidirectional capabilities and advanced conflict detection and resolution capabilities, you would want to typically choose an APN partner or a vendor from the AWS marketplace. In terms of pricing, compared to other solutions like pglogical or Oracle GoldenGate, this fits right in the center. With that, let's jump into a quick demo. Okay, so for the demo, we'll be actually taking a look at pglogical first. And for pglogical, what we do is basically we have two database clusters, DB1 and DB2. One of them is compatible with Postgres version 11.9 and the other is 12.4. The first thing that we need to do is, as a prerequisite, we need to go to the parameter groups. And you'll notice that I've created 4 custom parameter groups. 2 for each database cluster, and 1 is for the cluster level, so DB cluster parameter group, DB1. And similarly, 1 is at the instance level parameter group. And the changes that we need to do here before we do any sort of replication test is we need to update 2 parameters. So one of them is RDS dot logical replication. Set this to 1. I've already set it to 1 for my test. And the other parameter that we need to change is shared preload libraries. We need to include pglogical, which is one of the allowed extensions on Aurora Postgres, into the allowed value here. Similarly, if we go to the other cluster parameter group, we'll do the same changes. I've already done this here just to show you this how it looks like. And the other parameter is, of course, enable logical replication, set it to 1. Note that these parameters are apply type static. What basically this means is that you will need to reboot your clusters for these parameters to take effect. Now at the instance level, we have 2 different parameters. So DB1 instance parameter group. So here we need to just make one change, which is adding pglogical to shared preload libraries. I've already said this. And similarly for my DB2 instance parameter group, I will actually add pglogical as well. Once you've added it, saved your changes, you'll notice again the apply type is static for the instance level parameter group as well. So we'll go back to the dashboard, to the instances, and then we'll just reboot our clusters. And the way to reboot these clusters would be you select your writer instance, and from the actions dropdown, you can just click on reboot and then confirm. Okay, so my clusters are now rebooted, and you'll see the status change to available from rebooting once the reboot is complete. So for the next step, we'll be using Cloud9, and Cloud9 is basically a cloud-based IDE that lets you write, run, and debug your code with just a browser. It includes a code editor, debugger, as well as a terminal, and you'll see here that I'm using the terminal. So I've split up my terminal into 2 different panes. On the left, I'll be using for logging into my DB1 cluster, and on the right, I'll be using that to log into my DB2 cluster. The tool that I use to log into my Postgres cluster is going to be pSQL. And pSQL is a pretty lightweight, easy to use terminal-based command line utility that you can use to query your Postgres clusters. So the first step is to log into my cluster. So I'll log into my cluster using pSQL in DB1 on the left and DB2 on the right. You'll notice the server versions. So DB1 is 11.9, DB2 is 12.4. The first step is to create a user and grant that user super user privileges for us to go ahead with the replication. So the way we do this is I'll create a user pg user and grant the RDS super user privilege to this user. Similar steps on the other cluster. Once that's done, we'll need to use or create a table, test table for our replication purposes. And I'm just creating a test table, table1, pretty basic with an ID, int, primary key, an info text, and value int with 3 columns. And similar table will be created on the subscriber side. The next step is to actually insert some rows or insert some values into this test table. I'll insert some 5 values. So let's test what was inserted. I have these 5 values here. Notice that I'm not inserting anything on the subscriber side yet. So if I do a select star from table 1, there's nothing here. The way we'll fill in this table is actually going to be a one-way replication from the publisher to the subscriber side, and we'll see this in action. So the next step is to actually set up pglogical extension at the database level. So the way we do this is using the create extension command. That's done. We'll also do this on the subscriber side. So let me do that as well. Next, we need to create the publisher and the subscriber nodes. Now, nodes within pglogical are nothing but these are your Postgres database instances. And the way to create these nodes is using the create nodes SQL interface. So I'm just calling my node node1, publisher node as node1. I pass in the DSN. So these are the only 2 parameters for create node. Similarly, I'll create a subscriber node, call it node2. And now what I need to do is there's this concept of a replication set within pglogical. So replication sets provide a mechanism to control which tables in the database will be replicated, as well as which actions on those tables will be replicated. And these actions are nothing but these could be DMLs like inserts, updates, deletes, or DDLs like truncates. And the way you specify this is using the replication set add table SQL interface. Here what we are doing is we are basically adding all tables in the public schema to our replication set. And the way to do this is using the replication set add all tables SQL interface. Now once all the tables in our public schema are added, there's just one table, table1. So this should pretty much be replicated over to the subscriber. But then we are missing a step, which is where we need to create a subscription first. And the way to create a subscription on the subscriber side is using the create subscription SQL interface. So this creates our subscription. Note that we are just calling it subscription 1. The provider DSN is the DB1 cluster that we are using here as a provider. And the replication set is the default. So this is basically what we are using here at the publisher side. So now if I do a select star from table 1, I should actually be able to see the rows getting populated. So boom, there we go. We have the 5 rows from our publisher side replicated over to the subscriber side. Okay, so now that we've completed the initial setup, let's actually proceed by testing one-way replication. The way we'll do that is I'll try inserting one row into my table 1. See that it gets inserted, and also try to see at the same time on the subscriber side it gets populated. Similarly, if I try to update the same row, I'm updating the same row with ID 11 and I'm setting the value to 10. Let's see if it flows through to the subscriber side. All right, that looks good. And now we'll actually see if a delete can also work exactly the same way. I'm deleting the row that I just added. See that it gets deleted and the changes flow through to the subscriber side. All right, so that looks good. So one-way replication looks good. Now we'll proceed with setting up the bidirectional replication. And the way to set up bidirectional replication, there's just a couple of more steps to this. So one thing we need to do is set up publication on our DB2 cluster. So now because this will become a new publisher and this will become a new subscriber. So the way we'll do this is using the SQL interface. And the final step is to actually set publisher, the original publisher, as a subscriber. So we'll do this using this command. Note that the provider DSN in this case becomes your DB2 cluster, which is your new publisher or provider in this case. All right, so that should set up bidirectional replication. So now let's actually proceed with testing the bidirectional replication. So what I'll do is on my database cluster 1, I'll insert a value. Check the results here. So my new row got inserted. Let me also verify here. Okay, so the one way still works. Now let me do it the reverse order. So I'll try inserting a value here and see the value here first. So 30 gets inserted. Also see the value here. So 30 is also inserted. So it works both ways. So now actually with that in place, we see that the basic bidirectional replication works. Let's do a conflict test. And what we'll do is let's actually run an update statement on DB cluster 2. Now what I'm doing here is where ID equal to 1, I'm setting the value to 20. And similarly on host 1, I'm running a similar update statement, but I'm setting a value to a different value. I'm setting it to 30, where ID equal to 1. So you'll see that both of them flow through successfully. However, let's see which one is the final result on the tables, which one gets updated. So we'll see that the latest commit value, so this in this case, this is coming from the original publisher side or the new subscriber side, which was the most recent committed value, gets populated in both the sides. So you have your ID1 with value 30, ID1 with value 30. So that's the default behavior. So basically in pglogical, you get a number of conflict resolution options. By default, it is configured to accept the remote version of the change in case of a conflict. And you can always change this parameter by going to your RDS console and actually going to the parameter groups. If you go to the cluster level parameter and then search for conflict resolution. So these are the various values that you can actually set it to. The default value, of course, is applied remote, which is where the remote changes got applied and then the values got synchronized across both the sides. And that's basically bidirectional replication with pglogical. So for our Oracle GoldenGate for Postgres demo, we need to look at a few prerequisites. First, we need to enable logical replication for our source and target Aurora Postgres databases by setting the RDS logical replication parameter to 1. Second, we need to ensure the source and target tables for both our Aurora Postgres databases have the same primary keys. And third, we need to enable supplemental logging using add tran data and tran log options filter table parameter to enable bidirectional replication. Oracle has also published a pretty detailed blog on how to set up this on the Oracle side. So I've posted the link here. We'll also share this link in the description box so that you can go and follow along. Now let's jump into the demo. So for our Oracle GoldenGate Postgres demo, we have a cross-region setup where you'll see the region here on the left is Northern Virginia, which is my source. And I have a source database cluster called APG source. And on the right side, I have my target region, which is Oregon, which is US West 2. And the target database instance is called APG target instance. The cluster is APG target. So let's make sure that logical replication for my database parameter group is actually set to 1. So that's 1 here. I'll check the same on the target side. So that's set to 1. All right. Now on this screen, you'll see 4 terminals. On the left is my source, and on the right is my target. Top left is my source GoldenGate installation with EC2 instance. And on the bottom is I'll use this as a window as a terminal to query my Postgres source database. On the top right, I'll be using this to log into my GoldenGate EC2 instance. And on the bottom right, I'll be using this to log into my Postgres target instance using psql. So let's actually make sure on the source that GoldenGate processes are running perfectly. So I'll log into ggsci and then check info all. So this tells me that the extract and the replicate processes are running on the source. Let's also verify this on the target side. So ggsci and then info all. I have my extract and the replicate processes running on the target side as well. So with that, let's actually see what is in the database. So I have my psql client libraries installed here, and what I'll do is just see what we are starting with. So I have preloaded a set of tables here from a sample schema called DMS sample, and that has 16 rows. Let's also make sure that we are at the same page on the target side. So we are at the same starting point. So we have a sample schema with 16 tables loaded in both the source and the target side. Now what I want to do is, first and foremost, I want to test basic replication, and I'll start inserting data from the source and see whether it gets populated to the target. So let me start inserting value into one table. So I'll be using MLB data as my test table, and I'm inserting some values here, and I'll look for whether that gets inserted successfully on the source first. Yes, and the target. So yes, and you see the speed at which it got inserted. It's really near instantaneous. And what I'll do is, on the target side, I'll do the same test and try inserting some data here. I'll call it 201 and verify my data exists in the target side first. It does, and then on the source side. All right. So both the ways work, and similar is true for update as well as delete. Now let's move on to conflict detection and resolution. So psql by default has autocommit set to on, and for this test what we will do is set autocommit to off on both source and target. And there's one specific table that I'll be testing with, which is called ticket purchase history. And let's actually look at the schema for that on the source. So we notice that we have a primary key on sporting event ticket ID and the purchase by ID. And let's also verify the schema on the target side. I'll use this command. So \d is a quick and dirty way in psql. It's called a meta command to look at the structure of your table as well as look at the indexes, column level details, and so on. So this has the exact same primary key. So notice that we had a prerequisite of both the tables having the same primary key, so this is satisfied. So now what I'll do is try updating a particular row in this table from the source side. So what I'm doing is setting a purchase price of 30, where sporting event ticket ID is some number. Remember that this is not yet committed on the source side. And let's also view what is the current value. So we saw that there's 133 rows that got updated, and it's updated to 30. So the purchase price is 30. The transaction date time is now. So this is what we used. And I'll use the similar query, but I'll do a different update. So I'll update it to a different value on the target side. I'm updating it to a value 57 on the target side. This also updated 133 rows. Let's see whether the values got updated. Yes. And notice that the transaction date time is a little ahead. So this is the most recent timestamp that we have, and this is the most recent value. Now, if I press commit, so basically committing the value, let me commit it at the source first, and then I'll commit it at the target. Doesn't matter, it can be either way. Now let's actually look at the values at both the source and the target sides for this transaction. So there was a little bit of a delay there, but you'll notice that the latest value that we are using for the timestamp, that gets updated near instantaneously to both the sides. And this is primarily because we use something called as resolve calls to actually resolve this conflict. And the way it'll look like is, you can see this in your parameter files. So I'll look at my replicate parameter file as an example. So you'll notice that I'm using, whenever there is a row that exists on both the source and the target, in this case it was 73814821 with the ticket ID. I'm using a use max transaction date time. So whatever is the maximum transaction date time, that is going to be updated as the conflict resolution protocol. And this is what we saw here, where our value became 57 on both the sides. There are various other ways of handling this. There's good documentation from Oracle on this, but this proves that Oracle GoldenGate can now be used as a fully baked solution for enabling bidirectional replication for Aurora Postgres databases. To wrap up, I will leave you with a bunch of resources here to learn more about the various solutions we looked at in this session. So that brings us to the end of this video. I hope this was useful and you will take advantage of the various bidirectional replication solutions offered on Amazon Aurora Postgres today. Thank you so much for watching, and happy cloud computing from all of us here at AWS.